So, dear students, the topic of our talk today is on conditional probability, Bayes theorem, and discrete distribution. These topics are very important for any engineering students, especially in this institute. It is in third semester. Most of the batches are having this topic. Now, before going into the details of today's talk, the first thing which we will like to discuss is the contents. The contents of today's talk or an overview of this presentation will be like this. The first we will take conditional probability with example, then we have independent events, then follows with Bayes theorem with some examples, very preliminary examples just to illustrate the use of Bayes theorem. Then we have discrete random variable, probability mass function, which is a characteristic feature of discrete random variable. Why I am calling it a characteristic feature, I will let you know in due course. And probability mass function, distribution function, and then binomial distribution, which is a special type of discrete distribution with wide application in engineering problems, and example of binomial distribution. Conditional probability. As the name suggests, this probability is known as conditional probability. Why? Because the probability of the occurrence, or rather the outcome of an event, depends on probability of some other independent which has already occurred. That is why there is a condition on the present outcome or the probabilistic observation which we want to have. Now, conditional probability becomes very essential for some sort of studies where we need some prior information to predict some present results or some present experiments which has been done based on our prior knowledge. Based on those facts, conditional probability becomes a very important tool in the study of mathematical probability. Okay. Now, what is conditional probability? Let us try to understand. We consider two events, A and B, both connected with a random experiment. Now, these two events are actually both, you can say, consequence of some random experiment E, and that is why we are calling it connected. Now, second thing which we assume here is the hypothesis that the event A has occurred in a number of times, and the event B occurs simultaneously with A in A intersection B times in n repetitions of the experiment E. Okay, this is you can say the premises, or rather the assumption based on which conditional probability will be defined. Now, the ratio n of A intersection B by NA is called the probability of B, probability of capital B, even B, on the hypothesis that A has already occurred. Here, this part is very important. This part, A has already occurred. This part, remember, this is very important. This is actually the fundamental characteristic of your conditional probability, and it is denoted by PB by A. Now, based on our knowledge of probability, we can then define PB by A. This actually comes from the classical definition of probability. This definition now, PB by A, this one. PB by A then becomes equal to n of A intersection B by NA, and if we divide this by small n, the numerator as well as the denominator, then it becomes PA intersection B by PA, provided the probability of A is not equal to 0. Now, one may argue that this is the probability of event B when A has already occurred. Based on that, someone can say similarly, we can define probability of event A when the event B has already occurred. That means the reverse of this, you can say, to some point. Okay. Now, similarly, the condition probability A on the hypothesis B has already occurred is PA by B, which is actually equal to PA intersection B by PB, where PB is not equal to 0. Both these two conditions are important, otherwise it will not become meaningful. So this is the definition part of conditional probability. What I want to emphasize here is the fact that here occurrence of one event is depending on the occurrence of some other event, where both the events are part of this thin random experiment E. Next, we take an example to understand this conditional probability. This is a very fundamental example. It will help you to understand the basic facts and the rules which are associated with conditional probability in the definition which we have just now stated. It will be illustrated through this example. Example is, if one card from a pack of cards is drawn, find the probability of the card being a king of the spade. Okay, now in brief I have also written in the slide, you can see the solution. I will show you what we will get actually. Now, as we all know, the pack of cards contains 52 cards. 52 cards total. And there are 4 suits. Each suit contains 13 cards. Each suit contains 13 cards. So it is 13 into 4 is 52. And in each suit there is only one king. What we have taken as A is the event that the card drawn is a spade, and B is the event that a king of spade is the event B. Then we have to actually find, according to this question, PB by A. P B by A. Now, just now, as we have seen the formula, this can be written as P B intersection A by PA. Now, PB intersection A here means king of a spade. That is actually PB intersection A. Theoretically, it means king of a spade. Now, king in any of the 4 suits, there is only one possibility in all these 4 suits. So, here also the possibility is 1. And probability of A, what is the event A? A is the event that the card drawn is a spade. Now, there are how many cards? There are 52 cards, out of which 13 are spades. So, probability of A, I am directly writing this as 30. So, your probability of A B by A, that is the probability of a king from a spade, becomes 1 by 32. Okay, this is all about this question. This question gives us an important idea of how one condition actually we can say on one condition the occurrence of another event depends, both being a event from the same random experiment. That has to be true. Okay. Now, another implication you can say of the conditional probability is multiplication rule of probability. Now, what is multiplication rule of probability? Multiplication rule of probability plays a significant role in the later development of what we call the Bayes theorem also. Okay, now here you can see multiplication rule of probability says probability of A intersection B is equal to PA into PB by A, which can also be written as PB into PA by B, where PA and PB not equal to 0. As I have told you earlier also, this two condition plays a significant role, otherwise mathematically it will not be any meaningful equation. Okay. Now we come to generalization of multiplication rule. Now what does this say? For n events, if you have n events, a1, a2, an, then the multiplication rule can be generalized. That means this rule can then be generalized and we can write probability of a1 intersection a2 intersection an is equal to probability of a1 into probability of a2 by a1 into probability of a3 by A1 intersection A2. These are all actually conditional probabilities. And likewise, it goes up to AN, where the denominator is AI. I ranges from 1 to n minus 1. Okay, this is the generalization of the multiplication rule. This and this multiplication rule, sometimes we can say it is an implication of one of the main implication of conditional probability because of this term. Okay. Now next, come to an important aspect of probability which we call the independent event. Independent events. Okay. Now, what does independent event says? If for any two events A and B, probability of A by B is equal to PA. Okay. That means the probability of the occurrence of event A does not depend upon the probability of occurrence of B, as was the case in conditional probability. That is not happening here. It is becoming equal to probability of A. That is, the chance of occurrence of event A is not affected by the occurrence of the event B. The event A is then said to be independent of the event B, or more commonly we say probability of the event A and B are, means the event A and B are independent events. Okay. Now, the following theorem which I give is one of the most important characterization of the two events of being independent. And if you remember in your school classes also somewhere, or in undergraduate courses, in almost all courses where probability is there, this theorem is sometimes taken as a definition of independent events also. What does this theorem say? Two events A and B are stochastically or statistically, whatever you say, independent if and only if P of A intersection B is equal to PA into PB. Okay, so remember this result. This result is a fundamental result, sometimes taken as the definition of independent events also. Okay, now I have given in very short the proof of this theorem, which is a fundamental theorem. Let us first consider A and B to be independent events. Then from our definition, we know probability of A by B is equal to probability of A this implies probability of A intersection B by probability of B is equal to probability of A. From here, we can directly write this. Okay, so this is it. This theorem and this result for independent events. Now we take an example to understand this. Here the example is We considered the same example as one. In one, the example was, what was the example? The example was drawing of a king from the spade suit in a pack of in a full pack or a pack of 52 cards. We consider the same example. We can easily check the probability of drawing a king from a spade, which we have already done, was coming out to be 1 by 13 in example 1. And here you can see drawing of a king, simply king. What will be that? Drawing of a king. Drawing of a king of a spade was 1 by 13, and drawing of a king is 4 by 52, because there are four suits, each contains one king, and total 52 cards. So this is 1 by 30. So both becomes equal. So PB by A becomes equal to PB, you can say. Okay. And hence this is an example, a fundamental example, which you can say of a independent event. Now let us come to Bayes theorem. Bayes theorem again is an important theorem, not only from the probabilistic point. It has wide application. It has found its wide application in many other areas of engineering. For example, it is used to filter spam mails. Okay, spam mails which we all find in our mails, those there the name Bayes classifiers are used, which is based on Bayes theorem. Not going into the details, but that is one of the main important application area. Along with that, diagnosis, medical diagnosis is also sometimes done with the help of Bayes theorem and conditional probability in large. Now, what does this theorem says? If A1 to An here given set of pairwise, this is very important, pairwise mutually exclusive and exhaustive events. Then for any arbitrary event A such that A is a subset of this and PA is greater than 0, probability of A is equal to this. This is the first point of Bayes theorem. And in the second part, we have actually, you can say it is an inversion of what has been done in the first part. That is PAI by A is equal to PAI, PA by AI. Here one bracket I have missed, divided by PA, or I equal to 1 to N. These two are the main points which we wanted to state in Bayes theorem. Now, proof of Bayes theorem is again very interesting. I will give a sketch and try to explain as easily as possible so that the students can understand. Since A, the event A, which is an arbitrary event, is a subset of the union of these n independent pairwise mutually exclusive and exhaustive events, we can write A equal to A intersection this, which is equal to I equal to 1 to n this by distributive law. Now, after that, since A intersection AI is a subset of AI are mutually exclusive events, we have by addition theorem of probability, PA can be written in this way, which is equal to sigma equal to 1 to n this, and this can then be written by using the formula for conditional probability, this formula, or you can say this is actually multiplication law of probability. I have also written here a multiplication theorem of probability. Then we have PA intersection AI is equal to this. This implies PAI by equal to this, and this gives us the result. So this is the Bayes theorem, an important theorem in the context of fundamental probability. Now, I give an example to understand this. There are 3 ons. First on contains 3 red, 4 black balls. Likewise, something is given. Now, one on is chosen, and then a ball is, one on is chosen, and then a ball is drawn from the on. Find the probability that the ball drawn is red. Okay. Now, how to do that? You take first A is equal to the event ball drawn is red, and A1 equal to first term is chosen, first on is chosen, A2 second one, and similarly A3 is the third one. Now we use this formula, the first part, that is the Bayes theorem, which is that is this part. Probability of A is equal to probability of A1 into A by A1 plus this way equal on plus yes, in this way it goes on. Now a probability of A1, that is the first one chosen, will be 1 by 3. Then the second for PA2 it will also be 1 by 3, and PA3 it will also be 1 by 3. And what is probability of A by A1? A is the event ball drawn is red. Now we will have to count how many red balls in first turn. 3 red balls, in total 7 balls. So it will be 3 by 7. Similarly here you have second contains 6 black 2 red, so it will be 2 by 8. And the third one contains 5 red and 3 black, so it is 5 by 8. Multiply them and then you will get the result. And for the third one was chosen, supposing that the ball is red. Once you find this probability, use this in the formula, this formula, by considering AI as the red ball, and then you will get the answer. So I am not going into the more details of this problem solving. It's not possible also here. Now we come to discrete random variable and its distribution. Random experiment is with a sample space of a random experiment, a real valued function defined on S and taking values in R is called a one-dimensional random variable. Okay. Now discrete random variable. A random variable which can assume only a countable number of real values is called a discrete random variable. In other words, a real valued function defined on a discrete sample space is called a discrete random variable. Okay. Example: marks obtained in a test, number of successes in a trial. These are okay. On the other hand, random variable is called continuous, can take all possible values, integral as well as fractional between certain limits. Example: age, height, etc. Okay. So these are the classification of discrete and continuous random variable. Now I move to probability mass function. If x be a discrete random variable, the set of ordered pair is called a discrete probability distribution and presented in the following way. X is this and Fi is this. Here Px equal to xi equal to fxi equal to Fi. So the value of each Fi depends on xi. Okay. This function is called this function Fi's are called the probability mass function. Short it is written as PMF of the random variable x. A probability mass function has two fundamental properties which you must follow. All the probability mass function must follow these two fundamental properties, which are called Fi. All Fi's must be greater than equal to 0 and summation of Fi must be equal to 1. Okay. Now here is the distribution function for a discrete random variable. The distribution function of a discrete random variable is defined as a function fx whose probability lies between minus infinity to x, where this is small x actually, I mark this is small x, lies between minus infinity to infinity. Now if it lies in xi plus 1, then fx is the sum of all this probability. Okay. Now in discrete distribution given below, this is an example of this distribution function. This is the distribution given, and you see we have obtained fx. Now what is the underlying thing which you need to remember here is, because of this property, here 0 then 1 by 4 it is given here. For in this interval it is 1 by 4, and the next interval this 1 by 2 is added with this 1 by 4, and likewise, and the final one which you are getting is coming out to be 1. Remember this. Okay. So this is an example of distribution function, and next we move to binomial distribution. A discrete random variable is said to have a binomial distribution with parameters p and n if its probability distribution is given by this mass function. Okay, this is the probability mass function of a binomial distribution. Remember this. Okay, so this is probability mass function of a binomial distribution, which you can say the characterization property also of binomial distribution. Now, if X is a binomial distribution with parameters P and N, then its mean is NP and variance is NPQ. This is a standard result in form of a theorem. So students should remember this. Next, we take an example to understand how this works. And it's a simple example. The mean and standard deviation of a binomial distribution are given. Find the values of NP and probability at 0. Now we know NP equal to 4 from where? From the previous result where we have seen mean is equal to mu and variance is equal to NPQ. Okay. So NP into 1 minus, also remember one more thing, P plus Q should always be 1. So in place of 1 minus p, you can replace it with q, or q is equal to 1 minus p. From which we obtain this, this then gives us n equal to 12. To obtain px equal to 0, we use the probability mass function of the binomial distribution. Now the probability mass function, if you put I equal to 0, then you get this result, which comes out to be 2 by 3 to the power 12. This is how we can solve problems based on binomial distribution. Okay. Now that's all in this short presentation on fundamental area of probability, that is conditional probability, the Bayes theorem, also the independent theorem we discussed. We also discussed the multiplication law of probability. Bayes theorem was one of the most important aspects of this talk today. And then finally we ended up with discrete random variable, its probability mass function, distribution function, and then finally, binomial distribution with its probability mass function, and I have taken examples from all these areas. Okay, thank you all.